Okay, so we're going to go through this Trig review sheet, get this some solutions, and make a nice recording just to help you out. So let's go ahead and get started. So let's see here. Let me pull out my little workstation here. All right, so meteorologist. Find the height of a cloud using an instrument called a ceilometer. A ceilometer consists of a light projector that directs a vertical beam up to the cloud and it detects it. So let's see here. At Midway Airport, got the ceilometer with the base of 300 feet was employed to find the height of a cloud cover. The angle of elevation is 75 degrees. What is the height of the cloud cover? All right, so this is pretty straightforward, pretty easy one. So 300 feet, 75 degrees. And so we want to know what this is. So I'll call it y because up, down values y. I guess they use h, so maybe I should use h. And that's pretty easy. That's just a plain old right angle. So that's opposite, that's adjacent. So this is a tangent problem. So tangent of 75 equals opposite over adjacent. And so then h is equal to 300 times the tangent of 75. And if you're going to do this in your calculator, make sure your calculator's in degrees so you can get the right answer. If you're in radians, it's not going to be correct. So according to this, I get 1119.61, and of course this would be feet because the 300 was in feet. All right, so there's one down. Number 2, adorning the top of the Board of Trade building in Chicago is a statue of Ceres, the Roman god of agriculture. So the Board of Trade is, by the way, in Chicago. That's where they trade like stock options essentially for agriculture goods. So you can buy like futures and this and that on corn and soybeans and whatnot. So anyhow, so we're 400 feet away, and we do 2 observations, one to the base of the statue, one to the top of the statue, and you get the 2 angles as indicated. So their question is, what is the height of the statue? Okay, so I think if you kind of think about this carefully, we want to do this in 2 parts. So really there's this triangle. I'm exaggerating here. And I really want to know the height of this statue. Now the angle here is the difference between these 2 angles. So what would that be? That'd be 56.5 minus 55.1. You'd think I could do that without a calculator. But anyhow, that's 1.4 degrees. So I have that angle, I have that height, which is across from that side. But I really need like another side and another angle or something here, or maybe even 2 sides. Yeah, because if I'm going to use the law of sines, I have to have a side and its angle, right? A pair, which I don't have a pair at all. In fact, I don't even have any other piece of a pair, because these 2 are paired up, the ones I just wrote. But I need another pair to do the law of sines, right? And so that's not looking good. So possibly maybe law of cosines. And so after looking at it, I think we're going to tackle this with the law of cosines. And to do it, we're going to look at both right triangles. So one right triangle is like this, 55.1. And that's going to get me this side, which, by the way, is this side here. And there's another right triangle, the bigger one. 56.5. It's going to give me this side here, which is equivalent to that one, if that makes sense. So both of these would use what? Both of these are going to use cosine to get those hypotenuses. And once I have those two hypotenuses, hypoteni, I don't know, then I can use the law of cosines, because I will have a side angle side, and so that will allow me to then find h. So anyhow, so this would be what? So tangent of 55.1 equals adjacent over that hypotenuse x. Same thing over here. 56.5 equals adjacent over that one. So x is equal to what? That's equal to 400 over tangent 55.1. This is what? This is y is equal to 400 over tangent 56.5. So x equals, y equals, and I'm going to go out to maybe probably 3 decimal places here. So this one is, again, I'm in degrees, 279.044. So this is kind of messy. So not very nice numbers, but it's doable. 264.754. All right, so now that I have those two sides, and now I can crank out the law of cosines on this, because this triangle over here with the yellow pieces, that is not a right triangle. So I cannot use SOHCAHTOA on it, right? So I got to use law of sines or law of cosines. Okay, so here we go. So with that h and that angle, h squared is equal to what? If it's okay, I'm going to write just x squared plus y squared minus 2xy times the cosine of 1.4 degrees. And then I could plug the x and y values in, work this out, and then I'll have to take the square root of all that, right? And because it's a distance, we'll automatically take the positive square root value. And so just to make my life easier for writing, I'm not going to write all those values in for x and y. So let's see here. So square root of what? That would be 279.044 squared plus 264.754 squared minus 279.044 times 264.754 times the cosine of 1.4 degrees. And all that's under my root. And I get 272.22 feet. That does not seem right. So do I have a typo somewhere? You know what? My x's and y's can't be right. So this is not a bad example here. Why can they not be right? Well, if I go over my x's and y's are hypotenuse, they can't be smaller than 400. So I made an error over here. Something's not right over there. So adjacent over hypotenuse. Okay, so I must have... Oh, not tangent. That's what I did wrong. Oh boy. I said cosine. I think I said cosine, but for some reason I wrote tangent. It's cosine. Because it's adjacent and hypotenuse. Cosine. There we go. So, little things like that. So, they matter. But good thing I caught my mistakes. So, this is a good example. You know, just kind of rationalizing and saying, you know what, that can't be right. That can't be that big. So, something's not right. And then just kind of tracing my errors back. So, not cosine, or not tangent, but cosine. All right. That's better. So this one is 699.122. Much better. That's bigger than the 400. Makes sense. Good. And then the other one is 724.720. There it is. And then now I'll plug those in. So, oh goody, I got to retype all that fun stuff. So 699.122 squared, but it'll be worth it because I know I'm going to get it correct now. 724.720 squared minus 2 times 699.122 times 724.720 times cosine of 1.4 degrees. All that's under my root. Good, check. And so, much better. So 30.948 feet. So that's a pretty big statue, 30 feet, almost 31 feet. Okay. And so if you really wanted, you could Google that and see how accurate that is. Find out how big that statue is. All right, here we go. Moving on. 5'5" person standing 10 feet from a street light cast a 14-foot shadow. What is the height of the street light? So this is just real basic trig here. So we could find the angle x and do it. But some of you are pretty smart. And you notice we have similar triangles and all that. So actually we could do this with similar triangles and not even use any trig. But if you wanted, you could use trig. So one way to do it would be what? So we want to find the height of the lamp. So let's just call that L. So L is to 5.5 as what? That whole length of that bottom, which is what? 24, is to the length of the shorter piece on the bottom for the smaller triangle, which is 14. So actually we could just set up these ratios with similar triangles. Do it that way. And that lamppost is, what is it? 24 times 5.5 divided by 14. 9.43 feet. The other way is you could use tangent. And that would be opposite over adjacent. So then x degrees. So what are we going to do? We're going to do arctangent 5.5 over 14, right? So I get 21.448 degrees. And then we could now use that and say, oh, okay, so then the tangent of 21.448 degrees is equal to the lamppost opposite over the 24, which is the length of the big triangle, right? So you get the same answer, 9.43. Obviously, the similar triangles is easier. Okay. So, the American Ladder Company Association recommends a 75.7 or 75.5 degree angle between the bottom of the ladder and the wall. You are tasked with creating a table which will be glued to the side of the extendable ladder that your company sells. Complete the chart and generalize a rule for the distance between the bottom of the ladder and the wall. All right, so we'll just do one of them and then just kind of fill out the rest here. So if the ladder length is 8, and remember this angle is what, 75.5, distance between bottom and ladder of the wall, so that's this distance here, right? So this would be a what? It's a cosine problem. So cosine of 75.5 equals what? Adjacent over the length of the ladder. So 8 times the cosine of 75.5. So what is that? Um, 2.003. So distance between the bottom and the ladder and the wall. 2.03. So 2 feet if we round. Now the height of the ladder off the ground. So in other words, that's like the y value, which by the way, that would be sine. So it's the exact same equation, but it would be 8 sine of 75.5. So what is that? I get 7.745. So 7 3/4 feet, right? So that's what? Well, that would be 7 feet, and then 3/4 of a foot would be what? That'd be 8 inches, right? No, 9 inches. Oh boy. 3/4 be 9 inches. Okay, and so this is roughly 2 feet. Two feet 0 inches. Now, if you haven't already picked up on the pattern, when it's 10, it's going to be what? It's going to be 10 cosine 75.5, 10 sine of 75.5, right? So let's see here. Just going to work these out, and then I'll fill in the table here. So let's see here. For the next one, it's 2.5 feet. So that would be 2 feet 6 inches. I'm rounding to the nearest inch. And then 9.68. So that would be 9 feet. 0.68. So what's the 0.68? Yeah, I'll round to the nearest inch. So that would be 8 inches. And then 3 feet. And then 11.618. So 11 feet. And then 0.618. So if I take 0.618 times 12, I get 7 inches. So generalize a rule. We can see a pattern here. Every time I increase 2 feet, the distance from the bottom of the wall goes up by 6 inches. And then the height of the ladder goes up by what? It goes up by 1 foot 11 inches. So that would be kind of a general rule. So this is going to increase 6 inches. And let me move this. Cheat like that, and this is going to increase, whoops, So plus 2 feet plus 1 foot, 11 inches. All right, so there's kind of a general rule. Okay. Excellent. Let's finish this off. So some more trig stuff. So the average monthly temperature in degrees Fahrenheit for Juneau, Alaska can be modeled by this sinusoidal equation. So where x is the month of the year, January is equal to 1. What is the highest average monthly temperature in which month does it occur? So first of all, if this is a sine equation, it looks like this, right? So it has, as I call it, a center line. And then your peaks are going to be here, and then your valleys or your crests and your troughs is another name. Well, where's the center line? The center line's 40. Amplitude 16. So these are going to go up 16 from there, down 16 from there. So what is that? Well, the highest is therefore what? 56 degrees. So now the question is, when does that occur? So you could just be guessing and checking, plug that in. Another thing we could do is we could plug 56 in for y and try to solve, which is doable. It's a little bit ugly, but it's doable, right? Because I could say 56 equals 16 sine of pi over 6x minus 2 pi over 3 plus 40, right? So I could subtract 40. So what's that? 16 equals 16 sine of all that. And you divide by 16, so you get 1. Okay. So now what? Well, now you could take the arc sine of both sides, but you got a problem because it's sinusoidal. Sine, when is sine equal to 1? Well, sine is equal to 1 at lots of places, and so there's actually multiple solutions, and we could wrestle through that, and that's all fine and dandy. So, I mean, we could do that. I don't know. Or you could just flat out, work it out in your calculator. What is sine of equal to 1, by the way? That's at 90 degrees, right, is one solution. And so we could say at when? Well, if you take the arc sine of both sides, you're going to get what? Pi over 2, right? Arc sine of 1. And then the arc sine on the right-hand side, they cancel. And so then you get what? Pi over 6x minus 2 pi over 3. And then we could solve that. So let's see here. Oh, that would be parentheses. We got pi over 2 minus 2 pi over 3. Oh, no, plus, because we'll add it over. And then we'll divide that by pi over 6, right? And then I'm getting an x is equal to negative 1. All right. Which doesn't make a whole lot of sense. So that's saying January, or no, that'd be December. So that doesn't seem right. So, yeah, and then part of that problem is because of the sinusoidal nature here. All right. So that's not working so great. The other thing you could do is just think about the function. Think about the graph, right? Normally, sine starts right here, right? Okay. But it doesn't start there. This one, if I factor out, so if I divide out a pi over 6, I'm going to get an x minus 4, right? Yeah. Now, why do I care? Because, well, that tells me phase shift. And I can also more accurately do the period. So the period is actually what? 2 pi over b, which is 2 pi over 6. So what is that? So 12, right? Which makes sense. The period's a year. 12 months. Okay. All right. So that's good. And then the minus 4, that's actually a shift to plus 4. So instead of starting in so we know the period is 12 months. But it doesn't start here at January. It's been shifted over 4. So January, February, March, April, right? So this is April. And you know the peak is a fourth of the way through a period. So if the period is 4 or 12 months, what's a fourth of the 12 months? That's 3 months. So 1, 2, 3 more months is when you're going to hit that peak. So what? April, so May, June, July. So in the month of July. So maybe I made that harder than it needed to be. I don't know. But that's a way you could kind of reason your way through that. Okay, let's see here. Using either sine or cosine, write the equation of each function in the blank on the right. Okay, so D. Now, because we're starting right here, it makes a lot more sense to me to use sine. Okay. And it's been flipped, so I know that this is going to be a negative sign. Amplitude, we're going down to a 2, so that's a negative 2 sine, so I feel good about that. All right, what about the period? Period is 4 pi. So on this one, period is 2 pi over b, right? But because period is 4 pi, what's your b? 2 pi over 4 pi, or 1/2. So your b is 1/2, and it has not been shifted left or right. And so this is just 1/2. I guess we'll use x. And our center line was not shifted up or down. Actually, it's not shifted up or down on any of these. So there we go. So that's what I would do for that one. E, well, because we're starting right here on the axis, I would use cosine. So again, a period is 4, which equals 2 pi over b. So b is equal to what? 2 pi over 4, or what? Pi over 2. And amplitude is 2, so I would say this is 2 cosine of what? Pi over 2x. Okay, that's an easy way to do that. All right, G. Well, heck, that's the same graph as E, except it's flipped, isn't it? Looks like it to me. So I'll just flip it. All right, and then the last one, starting right here, and so this makes sense to use sine. it goes to pi, and so pi is my period equals 2 pi over b, and so b is what? 2 pi over pi, or in other words 2, which makes sense because the normal period is 2 pi. We ended at pi, so in other words, essentially we're going twice as fast, if that makes sense. And also it's a 3 for the amplitude because we're going down to a 3 from the center line. And it's also going down first, so this would be a negative 3 sine of 2x. And again, no left-right shift, no up-down shift, so keeping things simple. All right, last one. Suppose that the length of time between consecutive tides is approximately 12 hours. So that sounds like a period to me. So a period of 12.5 hours. According to the National Oceanic and Atmospheric Administration, or NOAA, Saturday, August 7th, 2004 in Juneau, Alaska, high tide occurred at 8:11 a.m. and low tide occurred at 2:14 p.m. So if you're thinking of like a sine function, right? High tide occurred at 8:11 a.m. and low tide at 2:14 p.m. And the height of the water tide was 13.2 feet, and the height of the water at low tide was 2.2. So this is 13.2, this is 2.2. Okay, find a sinusoidal function and model the data. So we got all sorts of good stuff going on here. First of all, I think it's easiest if we think of 13.2, 2.2. So what's the gap here? The gap is what? 11, right? So there's a gap of 11 here. Amplitude's half of that. So the amplitude, there we go, would be what? 5.5. Also, the center line is halfway through here. And so if you have an amplitude of 5.5, or you could average the two, or however you want to think about it, but that puts the center line at where? That puts the center line at 7.7. So I've already got a good chunk of my equation. An amplitude of 5.5 sine. Now, I don't know what's going on inside, so I'll be a little patient on that. And then plus, where's my center line? 7.7. All right, so now what? Period is 12.5. So 12.5 equals 2 pi over b. So b is equal to what? 2 pi over 12.5. And just because that's not the prettiest thing in the world, I'm just going to turn that into a decimal. If that's okay. And so I get 0.502. So my b is 0.5026. Okay. Parentheses x. Now left or right shift. Oh, crud, what do I do here? Okay. All right, now in a sinusoidal function, this is a quarter, this is a quarter, this is a quarter, this is a quarter. And so in other words, right, that's like half. But you know what? I don't even need to take advantage of that. If a period is 12.5, well, what's a quarter of a 12.5? So let's see, I'll do scratch work. I'll do it over here. So 12.5 divided by 4 is what? I get 3.125. So if I was to take 811 and subtract backwards a quarter, or in other words 3.125, or 3 hours and then seven and a half minutes, so we'll say 8 minutes, rounding to the nearest minute. That'll put me back to where this sinusoidal function starts. And so that would be what? That would be at 5, what? 5, I can math, 11 minus 8. I'm having a meltdown for a second here. That would put me at 503. And then to put this back in a decimal, 3 out of 60 minutes would be 0.05, so this would be 5.05. So I will say minus 5.05. Ka-ching. There we go. Whew. So that was intense. Use hours and feet as your units, and that's what I did. That's why I put those in the decimal places. Good. I feel good about it. So there you go. So there are your solutions to this review sheet. So I hope that's helpful, and you can look at the PDF of the solutions, or you have this nice video.